Can you hear me? All right. Okay, so the title is DIY, Do-It-Yourself Actors using Project Loom. And a little bit of background. So actors are a very useful and popular pattern, especially because it allows you to work on a multi-threaded platform, but treat your code like a sequential island. And because of that, you can freely mutate local state. And because of this property, very early on, Scala community is using actors. In the old Scala library, there used to be a actor part. Actor was part of the standard library in the old Scala version. I don't remember which one, which later got replaced by akka. And now, because of license change, there is alternatives like Peko, and there are other libraries also. The big libraries like akka and Peko, they go beyond local state management. And that is because they offer a lot more supervision, clustering, CRDTs, and distributed concurrency, basically, which is great and which is required for building some complex systems. But if your focus was the primary need of actors, which is local state management, you don't need all of that. So that is one assertion. So what we will discuss in this talk today is not any one library, but an approach to build your own actor pattern in a code base if your objectives are very modest, like local state management within the same JVM. You are not doing distribution. So that is the background. And what we are going to talk today, we'll start with the actor basics terminology. We'll adopt some terminology which is familiar or made familiar because of akka, like ActorRef. Then we'll talk about virtual threads, which Project Loom brings, and what is the role they play in your own pattern, or they can play. We'll talk of context interface. Now we're building up that if you do your own way, then suddenly you need more and more requirements that cannot be done by simply having ActorRef and a receive method. So context interface, which akka provides, which provides you a lot of helpers. So we'll talk about that. Then some pattern within actors like ask. It's very easy to implement, again, if your objectives are very modest. Future callbacks, which is a big topic in the akka ecosystem. There is a documentation that you should not mutate the local state in the future callback within an actor because that runs concurrently. We'll see how to deal with that. Child actors, again, a little advanced topic. Maybe you don't need that, but if you do, how do you extend the pattern for doing that? State machines, even within a single JVM, are very common using actors. So we'll take an example of that. Then we'll talk of, if time permits, we'll talk of a pattern. I call it Strand because it's like single sequential flow. And I will compare how different it is than actor, but suffices for some basic use cases. Okay. So to begin with, actor, as I said, the value of actor is the sequential execution. It's almost like in an island, you just forget that it's a multi-threaded platform. Within that part of the code, it's just like JavaScript, like there is one thread of control at any point in time. And because of that, modifying local state is easy, predictable, no race conditions. But to be able to achieve that, it needs some more parts, right? It needs a mailbox because external world is not sequential. External world are going to make concurrent requests to your actor, and you need a place where all this could be linearized, and that is the mailbox. And what is implicit and not talked about a lot is the scheduler, which will take these messages one at a time and schedule basically your actor so that you get a feeling that the messages are processed not concurrently, even though the platform is concurrent. So that is the implicit scheduler, which is scheduling these messages sequentially. Right. So as you can see, there are two sides which are visible. One is the actor.receive method, which is popular because of the old untyped actors, and the ActorRef.send, which is available to the external world to send messages to the actor. And with that, we define basic interfaces for our pattern. First is actor, which will have we'll use typed version because it's easy to do. So T is a type of a message this actor will handle, and then it will implement a receive method to deal with that. And then ActorRef will also be typed with T, and it will have a send method for that particular message. It will return you, instead of unit, it will return you future of unit, because again that is easy to do in the choice of implementation we have. And finally, you will need a mechanism to take an actor factory and then create ActorRef out of that. So those are the basics. So let's begin with implementing simplest possible actor with receive method, and let's call it a bank account actor. We have two messages, get balance and deposit, and our actor looks like this. So it has a receive method, and it is implementing it for type MSG, which is message type that we defined, having two possibilities. And in the receive method, we have implemented handlers for both of them. And then we can keep a var, which is a mutable state, and try to access it, read, write, basically, from within these handlers. So this is the kind of interface that we require in this pattern if you want to think like an actor. But if we just do this and don't create an ActorRef mechanism to access it, then that is meaningless, because someone will be able to instantiate this class, which is not correct. And if they instantiate the class, then they will be able to call the receive method directly, which is not good. And if they do it concurrently, then you will see that for these thousands of requests, those many different threads will be basically updating, trying to update the state. And that's why if you do it 10,000 times, and if you try to get balance, then there will be a race condition lost update, and you will get a count less than 10,000. So that is a problem if you just do, sorry. So we'll quickly have to do something about it and implement the ActorRef. In the process, we have to take care of other parts of the actor terminology, which is mailbox and scheduler, and we don't want to do it the hard way. So we'll take a big shortcut. Let's see what it is. So in Akka, ActorRefs can also be serialized across the JVMs. We don't need that because our use case is single JVM. And on the JVM, there is a nice toolkit, Java util concurrent, which provides you executor, and you can specify that this executor uses only a single thread. So you can create a single thread executor on the JVM. And this executor has a lot of similarities with the behavior that we want to achieve. And we'll compare what are the similarities, and we'll make use of this similarity basically to implement our pattern is taking a shortcut in a way. So let's see that in Actor in Actor you have this sequential flow, island of sequential flow. That is same for a single threaded executor, because you specified in the factory that you want a single thread associated with the executor. So it will always, all the tasks run on a single thread. You need a mailbox for an actor, but there is already a queue provided by the executor. Basically, it is internal to the implementation. You need a send method, which will take messages and put it in the mailbox concurrently, and it has to be thread safe. That is also given by the API, because the executor has an execute method where instead of messages, you put tasks, which are like functions, and they go and sit in the queue. An actor needs this sequential scheduling, which is also given by the executor. So there is a lot of similarity, and we'll make use of that. So the first observation from this is that actor.receive when applied to a message, is equivalent to basically creating a task. Yeah, in the two worlds, right? They are equivalent. Similarly, actor.send is equivalent to executor.execute on a task. Basically, they are equivalent. And if you stretch your logic, then you can implement ActorRef.send as executor.execute and a lambda which actually applies a message to the receive. So that's a very simple intuition, but yeah, I think once you do the comparison, it is obvious. So using this, we will implement the ActorRef, and it looks like this. So we take actor factory in the constructor, and we create an instance of an actor within the implementation, and then we implement the send method by applying the actor.receive on the message of the send, but we put this execution on an execution context that we create, right? We create. And how do we create that? We create it using an executor, which is Executors.newSingleThreadExecutor provided by the JVM. So in a sense, the send implementation is same as Executor.execute and the lambda for the receive. So that is the simplest implementation you can have for an ActorRef, and we can quickly check that. But before that, we also need to combine the two worlds. Given actor factory, we need to create an ActorRef, and that can be done by just having a spawn method in something called actor system for now, and then delegating it to the implementation that we just had. So if we now check the same code that we were trying to do, first of all, we are not going to create a new instance by our own. We will use actor.spawn and then give the factory, and then it will create the instance for us, that is the reason we get ActorRef back instead of a account actor directly, and we can't call the receive. We are not doing any effort to prevent users from not accessing or not creating an instance, but that can be done later. And then if you use the ActorRef.send and repeat the same code, then you see that all the execution is happening on the single thread for all the 10,000 entries. And if you make the same call, then you won't have any lost updates. So race conditions are removed. So that is the one part of the implementation. Now we can bring in virtual threads in the picture, but before that, let's see that I was saying that if you use this mechanism and spawn a lot of actors, then you're going to use so many threads. And then one of the nice things about akka-like systems is that they're very lightweight. One actor doesn't map to one thread, but it's just an event based and not thread bound. So we'll solve that problem again, taking a shortcut. But first, what are virtual threads? So Project Loom, which is going to be generally available in Java 21 next week, is available now as a preview. And if you use Java 19 onwards, you can try that. And what do virtual threads give us? They provide MN scheduler, which means that a lot of virtual threads can be scheduled on a small number of platform threads. And when you block a virtual thread, then it actually gets suspended. For example, if it's waiting for I/O to return a result, it will get suspended, and once the results are back, it will resume. So that is all taken care and given by the platform. And it also gives some new APIs. Two of them are of interest to us. Right now, only the first one, which is a factory, builder factory, and it allows you to create a thread factory for virtual threads. And then the other one we'll use later. So using this, right, we see our existing implementation where we are using a new single thread executor API. It also optionally takes a factory, and we are just going to provide this factory, which is thread of virtual.factory. And by virtue of doing that, the threads that it will spawn will be virtual threads, and we can just confirm that. So if you run a small test for spawning 15 actors, then you see that there are all these threads are virtual threads, and they are being spawned on a small number of maybe 16 odd platform threads, which are equal to the number of cores on this machine. So this one nice property of actors that they are lightweight, or they were always lightweight. We achieve that by simply plugging in a different factory in the executor. All right. So we'll move ahead. So if you do this pattern, then slowly your needs will grow, and you would want to make use of underlying execution context, or a way to stop an actor, or do a few more things. And Akka has a pattern where the context gets injected in an actor, and then you can make use of that. So we'll follow the same pattern here. What it will enable for now is stopping and execution context, and then eventually we'll build timers and self-reference in child actors and so on. So this is our current interface for actors, and we'll take the context in the constructor, and we'll use using parameters so that user don't have to give it a name. They can just use a type. It will be obvious in the next slide. But the implementer of the actor will have a name called context, and they can use methods on that. And for now, we'll have only 2 methods. So again, this is a kind of a refactoring which I'm trying to animate. So this is our existing implementation, and what we do is we separate out the executor part and the send method part, and we put send method. We keep send method inside the ActorRef, and create a new implementation called for the context interface, where we provide the implementation of execution context, because that is one of the APIs. The implementation of ActorRef now takes few more parameters required for the refactoring, and we have one method available, and the second method we just add by executor.shutdown. So it's very simple, but I'm trying to just refactor the code in the slides. Hopefully the snippets are available on the GitHub. Hopefully it should make more sense if you yourself have a look at that. The spawn method also needs some change. Now that we have a context injected automatically in all the actors, we need to change the spawn method to take the context function, which is a nice thing in Scala 3, and there the context will be provided implicitly, and that is again going to be easier on the end user when they use the spawn. In fact, for the user, the spawn method will not change at all. We'll see that. Using this factory, we create the actor, we create the context, and then delegate it to the ActorRef implementation. So this is some refactoring, and then our actor looks like this. So the only change user is doing is in the constructor of the actor, they are expecting using context, and that allows them a handle to basically a context method, where they can say context.stop on a new message that we add and clean up the resources stuff. So this is the 2 parts we implemented: execution context and stop. We'll make use of execution context in the next. So ask pattern, right? This is a simplified request response interaction, request reply interaction on top of send. Akka has that. It needs an additional sync parameter in all the messages, which needs to be used as part of ask, because the actor handler will send the response back via this sync, and that is a known pattern. Akka type has that, and Akka uses ActorRef as this sync type. But we will use promise of T because it's simpler. Single JVM use case, it suffices, very easy to implement. So this is the signature of a akka ask pattern, where ask takes a lambda, which will construct the message of type T using a ActorRef sync. But we use the same, but instead of ActorRef, we use promise. And the implementation is really simple. The pattern using promise is that you create an instance of a promise and return the future associated with that, and then basically pass that promise by constructing the message first using the factory, and then delegate it to the send method. So this is the implementation of the ask pattern, and you can use it. But to be able to use that, you need to make changes to the code, existing code. So now get balance, which is like a method with a message without a parameter, now we'll have to take additional parameter, as we said, response promise. And so that is the first change that will be done by the implementer of the actor. Implementer of the actor will also have to send the response back on that promise sync. And the user will have to use lambda syntax and this pattern is exactly similar to akka. If you have used ask pattern in akka type, this is exactly what you will do. So these are the 3 changes you'll have to do, and we achieve that. All right. So akkas, if you have a context in your akka-actor, and you import execution context, then that is not tied to the actor's control flow. It is bound to the global fork join pool. So because of that, future callbacks must not update actor's mutable state, and that is the official recommendation from the akka documentation. Because these handlers, actor handlers, and the future callbacks, they run concurrently. Actor handlers are sequential with respect to each other, but the callbacks of the future are running on completely different thread pool, and that's why they can run concurrently. So it's required that you never do that. Otherwise, there will be race conditions. But we have chosen a design where it will not be a problem, because our whole design is based on a single-threaded execution context, which is the control flow for our actors. And we can easily mix both. So let's do a demo of this. Let's say that we add 2 deposit methods. One is the regular deposit, and the other is via callback on a future. And both of them are updating the balance, right? And we are using akka-like execution context, which is equivalent to execution context.global for all practical purposes. Then if we do concurrent operations on this ActorRef by sending deposit and deposit via callback concurrently, you will have the same issue, right? And if you ask for a balance, it will be less than. There will be lost updates because it's no more thread safe, and things are running concurrently. Line 11 and 15, 11 and 14 on the left, they are concurrent. But for us, if we just change it to the context.execution context that we have created, then we are back, right? I mean, all the future callbacks as well as the messages, they are running on the same control thread, same virtual thread. All right. Timers. So you need a way to schedule things within actors so that you can send messages to yourself, to other actors, and there are variations. You can have a schedule method for single event, or a periodic schedule with initial delay, or schedule exactly on that time, and so on. We are going to implement the simplest version, which is a single task scheduling without any delay. And you can do all kinds of things. Akka recommends you use this only to send messages to yourself or other actors, but we can also update the local state, and there won't be any rest conditions because of the same reason that we looked at earlier. The implementation is again simple. You have the same method signature that akka uses, one of the variations, and what you do is, instead of new single thread executor, you use a new single thread schedule executor, which allows you to schedule, right? But you still have a single thread executor, and if you do that, you get executor.schedule, where you can schedule your tasks, and they will run in the same control thread as the rest of the actor. And then this should be cancelable, so you can also return basically a implementation of cancelable by just delegating to future.cancel. This is Java's future, and then that is so we'll see the example of timers along with the next topic, that is self-reference. So how do you refer to a current actor that you are within, so that you can send messages to yourself or pass your reference to other, right? So this is similar to this in objects. And this is called as self. The name is self in the akka ecosystem. How we implement that? Well, this introduces further complexity. So far, our context interface doesn't have any type parameter. But now self, we have chosen actors to be typed. So self will also have a typed ActorRef. And because of that, we need to first do that change, that take a type parameter in the context. And right, so we need to introduce the type parameter because self is an ActorRef, and you need to do that. But there's more complexity. Now your implementation of the context itself needs to take the actor factory, because you need to hold that reference within the context, because context.self can be called anytime. So it becomes a member, and that's why constructor, instead of spawn method, now the constructor of the context needs to have that factory. And the implementation is not complicated. I'll not repeat. We are just moving some of the code earlier now within the implementation of the context. So that is the implementation. Now we'll take an example where we use the, I'll keep seeing here so that I know when it goes blank. So now we'll take an example where the timer and the self-reference can be used together. So let's say that in this example, I schedule a message to myself, a stop message to myself after 10 seconds after I get created. I mean, it's a crazy example, but simple to demo. Then in one of the handlers, I choose that, okay, if I get a deposit call, any deposit calls, then I will just cancel the timer. So I should be able to use timer.cancel there. And then the stop method, the stop message that I've sent myself, in that I can use the context.stop and clean up the resources. So this is basically idiomatic way of scheduling things, sending messages to yourself, never doing a state mutation within a callback of the schedule method. But within the schedule method, it's perfectly fine if you also mutate the state. We are not going to do that, but yeah, I think that is perfectly fine in our case. All right, so I'll move to child actors. So this is if you do need that hierarchy. So actors can spawn. I mean, that is the key part of the actor, that it can spawn other actors called child actors. And because of that, there is a hierarchy, right? Parent-child goes on. And stopping the parent actor does the cleanup and stopping of all the actors recursively. And parents can also supervise the child actors, but that is out of scope. We are not going to talk about it. If we extend this philosophy, then actor system actually becomes the root, because that any actor, top level actor, must be spawned via actor system, and that becomes the root of the hierarchy or parent of everyone. And then if you stop the actor system, it should recursively go and stop all the actors. So let's see how to deal with spawn method. So spawn method needs to take the actor factory, but it adds a lot more complications now. So because of this hierarchy, we need to track parents, because if we don't have reference to parents, how will a parent we won't have the full hierarchy, and we won't be able to stop or remove yourself from the parent list. So the implementation is relatively simple. You create an instance of the context. You keep a copy of child context with you, and then add that child context, created context in that set, and return the self-reference. So that is the implementation, but now it became complicated, because now notice that this is not thread safe, right? This is by design. This will have all kinds of problems if this method was accessible outside, and that is true for akka context also. So akka context is very specific to the actor that you are working with. You're not supposed to basically pass around context of one actor to the other, and if you do that, there are all kinds of problems. So it is true here also, because the context is always supposed to be used from within the body of the actor. So we don't have to wrap it in the execution context. We just do the plain mutation operation here. Stop method will go and recursively stop all the child contexts. Will remove its own reference from the parent, and this is where the race condition can happen, because multiple children will have the same parent and they will try to remove their references. And if we don't protect remove, so now that's why remove is protected by a future, and that future is scheduled on the execution context, which is single threaded. So it's a callback we are doing, but it is on the actor's control thread, so that is safe. And then we shut down the executor basically that we have created. So that is stop. We also need something called actor system, which has some nice utilities. The first is that it gives you a global execution context. Now, not a single-threaded execution context, but if you are running a program and you need to access basically the execution context that where you can run your tests and top level, then you need a execution context at actor system level. You need a spawn method to spawn the top level actors, and you need a stop method to stop the world. Now you notice that the spawn method is, instead of returning ActorRef, it is returning future of ActorRef. Again, the API is similar, that in akka-actor system, the top level actor, when you spawn, it returns a future of ActorRef, and that is because this needs to be protected. I mean, the implementation will access the spawn of the context, and if you don't protect it, it will be a problem. So we'll see how to implement that. But before that, we implement the execution context using the another API that we mentioned initially from Project Loom, which is new virtual thread per task executor, which means this is a global executor, but we don't restrict to we don't directly use the fork join pool ourselves or number of cores. We just say that for every task that gets submitted to this top level execution context, there will be new virtual thread that will be spawned. And that is perfectly fine because virtual threads are lightweight and they can be as many as you want. The spawn method itself will require you to create a root context because actor system is the root of everything. But it doesn't need actor factory, so we keep it null. It doesn't have a parent, so we keep it none. But we use the spawn method of this root context to create the top level actor, but ensure that it is created using the execution context of the same actor, right? So that's the trick, and that's why the return type of spawn method is a future and not simple ActorRef. I think one of the benefit of doing this myself or trying this yourself is that you will also appreciate why certain APIs in Akka look the way they are, right? Spawn method inside the context is different than the top level spawn method, hopefully. Stop is simple. You stop the context and the executor. So that is about the child actors. We'll look at a state machine example. So actor behavior changes or can change based on the state, right? And it's a very useful pattern for actor-based applications. So we'll pick up an interaction pattern which is mentioned on Akka docs. It is called as buncher actor. It was blog posted long time ago when Akka type came out. What it does is that it buffers a burst of incoming messages, and then so all these command 1 and 3, these arrows, they are the incoming messages. It will batch it, buffer it, and then send that batch to the target. And then it does that action of sending either on one of the two conditions, either there is a timeout or when the size of the buffer exceeds, right? So this is a good example because we'll be able to make use of some of the things that we built and also a full-fledged example, hopefully. So there's a lot of code, but I will focus only on few things that we don't get nice DSL that Akka type gives you, behavior and all that. So we have to do the state handling ourselves for the state machine, and we use a var is idle. So initially the state of the actor is that it is idle, and then in the receive method we put if then else, saying that if it is idle, then use the when idle block, and when it is active, then use the when active block. And then the implementation is captured in both these methods. So when you are idle, if you get a message, you put it in a buffer, but then you immediately start a timer. When the timer expires, you send a timeout message to yourself, and we'll make use of that later. And then you change your state to active by making this flag false. And when you are in the active mode, if you get a timeout, you send a batch and then become idle. So this is like target.send and then resetting all the vars. But in the active state, if you get a message, then you buffer it and you first see if the batch size is met. If it is met, then you cancel the timer and send the batch again and become idle. So this is like a almost one-to-one translation of the documentation which this pattern talks about. All right, so this is the test. I think in the interest of time, I'll just skip a little. It works. I mean, that is the test, right? So, but I will touch upon my favorite thing. I mean, it's not very safe, but I like it. I use it. So Strand pattern. This is the same behavior, right? But it's unlike actors because it's not using messages; it's using methods. And once you know that you implemented your actor in certain way, you think that, okay, just it's one small step away from just using methods instead of messages, if you follow discipline, of course. So there are no ActorRefs, there are no self-references, the plain Scala object, so implementation becomes a lot simpler. But you need to follow a lot of discipline. You need to ensure that all these publicly accessible methods are scheduled on the execution context that you have created. And if you follow this pattern, it's very useful, but mistakes can happen, which are rare, basically, if you follow the discipline of messages. So I have few slides which will just compare, and I will again focus on the deltas. So if you see, I have this account actor implemented in two ways. And you see that there is no actor interface, there is no receive method to implement, right? So it's just account. Instead of taking a context parameter, it takes a parameter, I call it Strand, just to distinguish. Both of them have the execution context, single-threaded execution context, very similar. They have mutable variable, private. And one of them is dealing with messages. The other one is basically using the future callbacks, because these future callbacks are happening on the same thread of execution, which is the execution context. And deposit will look like this. So suddenly this right side looks a lot more familiar, but you have to follow the discipline that all the public methods must go via these callbacks, otherwise they will be a race condition. So this is you can make mistakes here. The implementation of the Strand is also very simple. I mean, so in fact, you don't need the factory because there are no self-references. You don't need that factory. You need to maintain set of children if you want to recursively stop them. Spawn method becomes simpler because instead of returning ActorRef, it directly gives you the instance of the type. So this is much simpler. Actor system and Strand system, again, very, very similar, very small differences. And let's look at the application. So I create an instance of actor system versus Strand system. So in actor world, I use the ask pattern to get the balance, a future of that balance. Here, I just call the get balance method. That will also return me a future of balance. Same for the send. Right, send in our design returns a future of unit. Here it will return directly. You can make a call to the method, and so on. So I think, and then finally, you can also implement the state machine using Strand. I will just skip that totally, and I will go to conclusions. So actor as a pattern can be used without a library. I hope I managed to convince you. It allows to work with islands of sequential execution, and it's a very useful and a general pattern. Loom provides this virtual thread, which makes it lightweight. So some of the criticism that, okay, your actors are heavyweight if you implement it yourself goes away, but they are not essential. In fact, virtual threads are not even available generally, right, till next week, but we can still, without them, the pattern, I find it very useful. And this act of DIY actually allows you to be minimal. You can pick and choose what you want, just enough what you want. And for example, child actors, we don't usually need that that level of sophistication, we don't implement that. Strand is an interesting variation of the same thinking. You get the sequential execution, but no messages. And I would say it is the simplest alternative in this DIY thinking that we are doing. Akka-actors offer a lot more, and they are a complete toolkit basically, right, for distribution, etc. And if you have to deal with cluster programming, then you should just go for that. And there is also Lehigh's caster library, which is the tiniest actor library, and I think it's yet another implementation of the pattern. You can it's like all the code can be inside a single file. So check that out. That is it. These are the code snippets, and thanks.